All right, let's talk about relational algebra. Right, so just like there was a mathematical foundation for computing and algorithms in general before there were even computers and CPUs and whatnot, there's also a lot of mathematical foundation on the fact of being able to represent data using the relational model, right? So early on, in 1970s, Edgar Codd, while working at IBM, he was at the beginnings of the relational database looking for mathematical foundation for this new idea of having to break up large data sets into constituent tables and rows and then having them related to one another. And so a mathematical foundation was created that would allow you to create equations that represented relationships between tables and how to operate on them, right, in such a way that would allow you to perhaps have mathematical expressions that will allow you to generate proofs that that database was sound, right? That represented some phenomena, some real phenomena. Very much like other engineering fields have equations that allow them to operate on them, right? And make sure that that building is not going to fall, right? That it meets certain requirements, that it's within certain constraints. So same thing. We were looking for a formal understanding of relational databases. The basic data representation was the table, right, and rows within those tables, and various operations that we would like to use to operate on these data sets. We'll look at first at single table operators, things such as select, being able to retrieve records from a table given a particular predicate, right? Meaning you might have millions of records, of which probably you don't need all million records. Probably you need a very small subset of those records. So which records do you want, right? So select would allow you to filter and retrieve all the ones you really cared about. Then project allows you to filter out the fields that you might not want. Right? Select returns all the fields of all the records. Allows you to filter vertically, right, and say, well, out of all the records, I only want these records. Whereas project allows you to filter horizontally, right? It says, well, which fields do you actually want? Do you want all of them, or do you just want a subset, right? So together, select and project allows you to pinpoint exactly, which records and which fields do you really care about. Sorting, as the name suggests, allows you to order it in a particular way, mostly for convenience. Our human brain, parses things when they're sorted in a particular way. Not that the data set underneath, when you store it, has any particular order. Right? You should not assume that the data, when it's stored, has any particular order. It's like sets, right? In a set, there's no ordering, right? Later on, we'll talk about. For optimization purposes, we might want to sort it, right? Might want to create indices, right? That provide the data sorted in a particular way, just like you would sort a phone book, right? If you want to find something by a last name, right? But if you have a phone number, the sorting by last name is kind of useless, right? So you might want to sort it also by phone number, right? So depending on how you want to search it, you might want to create different sorts. Right? So we'll talk about indices a little later. A couple other additional operations. You have a rename, where you can rename a field, where you can rename the name of the table. These are very useful, especially if if you want to change the name of a field from something very cryptic to something useful for human consumption, or even if it's a field that you wanted to repeat it multiple times, right? Where you might have a field that's a foreign key and a primary key, and in a query you want to join the same table with itself, right? Like a self join. Where you might have fields repeating multiple times, you have to rename them because you cannot have fields having the same name. You have extend. Extend allows you to calculate fields on the fly, right? Being able to say calculate and maybe concatenate two fields to make a third field, right? Maybe a field such as maybe the full name. A full name might make no sense to store a full name as part of a table, since it would be a redundancy. Since you already have the first name and last name, it would be a functional dependency to store also the full name, right? Because you might have some inconsistency. What if you change the first name but you forgot to change the full name, right? That would be a perfect example of using extend, right? Where you could generate an extend field called full name, which is a concatenation of two other fields, the first and the last. Yes? So extend allows you to calculate fields on the fly. GroupBy allows you to look at records and see which records might be able to be grouped by a particular predicate, by a particular criteria, right? Maybe I want to find out, what are all the students for a particular course, so I can group by course, right? And I can ask questions about the entire class as opposed to ask something about an individual student. I might want to ask questions about the particular class. What's the maximum age? What's the average grade? I can ask questions about the group itself, right, as opposed to individual. So GroupBy allows you to do operations such as that. You also have operators that operate on multiple tables, right? Typically by two. You can operate on multiple tables, but they can all be written in terms of operating two at a time, right? Two tables at a time, right? So in particular, we'll see a product. A product is an operation that, given a set of records and given another data set, right, we consider all the possible combinations of all the records, right? And this is useful to think about, what happens when you are searching for data, right? So you have a data set. What do you typically would have to do to find something in that data set? You have to loop through it, right? You have to consider all possible values, all possible records, right? On average, things will be somewhere in between, right? It'll be unlikely that it's the first. It's unlikely that it's the last. It's somewhere in between on average, right? It's n over 2, right, on average. So what happens if you actually have records from one table that are somehow related to records in another table? Well, you need to have two loops, right? One that loops on one of the tables, and as you're looping through one, you're looping through the other one, right? Once you're done, then you advance the other, so you loop again, and you loop again, right? In either case, it's n over 2. But since one is nested inside of the other, it becomes quadratic, right? So basically, you're in theory, you are considering all possible combinations of all data sets, all data points in one data set, combined with all the data points in the other data set, all the possible combinations. Some of those combinations might make no sense, right? Because some of those foreign keys are not referencing some of the other primary keys, yes. But you don't know that a priori. You have to go and loop and search until you find it. So there's a whole bunch of them that didn't match, but you had to loop through them anyway, right? So you had to consider them as possible combinations. So that's what product does, right? It represents the fact that you need to consider all possible combinations of all the data points in one data set with all the data set points in the other data set, right? And then when you join is the fact that you don't really want all the possible combinations. You only want a subset of all the possible combinations. Which one do you want? The ones that are actually referencing each other, right? The students that are actually in that course, not students that in some other courses that they're not enrolled in. I don't care about those, right? So what join does is that it's a combination of a product followed by a select, meaning it's a subset. I'm filtering. I only want the ones that actually have references to one another, right? So a join is basically a product followed by a selection, right? And that's such a common operation, right? A product followed by a selection that it has its own name, a join, right? Then we have a semi-join, anti-join, and several other types of join that are different variations of the join, where join only considers the one that match, right? Whereas semi-join and anti-join and whatnot are considered the ones that don't match. What happens to the records that didn't match? Maybe I want to look at those, right? Or maybe I want to look at the ones that match on the left-hand side, and I want to look at the ones that also didn't match on the right-hand side, right? I can retrieve the ones I want, right? And we'll see why would you ever want to do that, right? There's some cases where that matters. We have also a union, right, where it takes the retrieval of a particular data set and unites it or concatenates it with the result sets of some other selection. Anyway, so let's talk about queries. First, let's look at queries. So the most basic one is us wanted to be able to retrieve data from a certain set of tables. So the syntax is select followed by the data set. In this particular case, it's a table, but it doesn't have to be a table, right? It could be another select inside, right? You can nest selects one after the other, right? But in any case, it's a data set. It's a provider of data, of rows, right? In this case, is a student table, which provides a whole bunch of rows, and then followed by a predicate, right? So I want to select all the records in the student table that meet this criteria, right? So this is the syntax. This is the mathematical or the symbolic representation of the same thing. Sigma followed by the predicate and then operated on that particular table. Right? You can combine and make the query and the predicate more complex using Boolean expressions, ands and ors and parentheses, right, to be able to combine various Boolean expressions. And this is the graphic, the symbolic representation of the same query, right, where you have the predicate down as a suffix. You can nest queries, right, where the output of one select statement could be the input of an outer select statement, right? So for instance, here's students who graduated in 2004 with a major of 10 that are either on 10 or 20, right, chemistry or math. So first here we're retrieving all the students for a particular graduation year, and then that's being fed to an outer select statement that filters it by major either 10 or major 20. Here notice that what we're doing here is that we are naming this query, right? We're associating it to this name. See that? Right, so that we can reuse that name over here. That's the introduction of what we'll look at next time. We'll call it a view. Right? We can name queries. This is a named query as the name Q1, which we can then later on use it as if it were a table, an actual table. Right? So those are views. You can also oftentimes represent the query graphically, right? And very often this makes it easier to look at and visualize what's happening and how the data flows. Right? Oftentimes it's very useful for optimizations. Right? Usually in a database, you can ask the database to calculate the plan. Here's a query that I'm giving you, and then the database needs to compile your query. Right? It has to say, okay, well, this is what I'm going to do to be able to retrieve the data. I'm going to fetch some data from this table. I'm going to join it with that other table over there, and then the result of that, I'm then going to join it with that. Right? And it can graphically represent for you, right, what the database is about to do. Right? And oftentimes we look at it and we might identify some optimizations that we might want to do. Right? If we move around some of the joins, right, some of the queries don't have to repeat over and over. Right? So graphs allows us to capture that kind or identify that kind of information. So project allows us to filter out from a particular query, from a particular table, and identify only the fields that we care about. For instance, here we want to retrieve information about the student, all the student records, but I only want the student name and the graduation year. I don't want all the fields, right? And then you have the mathematical representation. You can combine these, right? For instance, you can have the inner select. Select all the students that match a particular major. And then the output of that can then be the input of a project where we're only keeping track of only the student name. This is the most basic select you might find in SQL, right? Where you have a select S name from student where major ID is equal 10, right? So this is finally something that might look similar to what you might want to implement using just plain old SQL, right? SQL. So here, we symbolically we can write it this way. We can also graphically represent it using this tree, or representing it using a combination of tree and the equations. Some queries you have to be careful might not return anything, right? Because the inner query, it might filter out records or filter out fields that outer queries might need. Right? So for instance, here we are, the inner one is retrieving only the column or the field student name, but the outer query is the predicate needs to match against the major ID. But I don't have the major ID, right? Because I'm only projecting the name, the student name, right? Also, even though project doesn't have a specific equivalent in SQL, well, it does, right? When you specify the fields that you want, right? That's basically a project, right? A projection, right? That you're specifying the fields that you want, right? In other databases, MongoDB and other databases, you actually have specific operators, right? Called project, right? Or Mongoose, I'll see a little later, right? You can specify exactly which fields you want, right? So they have operators called project, and then you'll know from where the jargon comes from. Sorting allows you to retrieve data from a particular table and then order it by different fields or combination of fields. Again, this is only for display purposes, not that the data should be considered sorted in any particular way. Rename, as the name suggests, right? It takes the particular field in a particular table or query and just renames it to a different name. Extend allows you to create a brand new field. I'm not sure what grad class is listed. Yeah, that's where it should be. There we go. Is that better? There we go. So we're looking at the student table, and we are doing a calculation on the fly for each record. We're calculating what graduation class are you? Are you the first graduating class, the second, the third? So we're calculating when you graduated minus the year that the school was founded, and then we are creating a brand new field called graduating class. Right. All right. GroupBy. GroupBy allows you to take a table, right, and look at fields that might have the same values, right, and be able to group them by that particular field, right, that they might be somehow related to one another. Maybe we might work in the same department. Maybe we're all registered in the same course, right, and we like to be able to group by that particular by that particular field, right, by the course or the section or the department that we're in, and consider us as part of a particular group. You can group by any number of fields. You can group by you can group by no fields, by a particular field, right? 1, 2, 3, any number of fields, and then what will happen is that wherever values of a record matches for that particular field, they'll be considered in the same group. They'll be collapsed into a single record, right? And that means that the individual values for the individual fields are not going to be available, right? They're going to be gone, right? We don't have them anymore. Instead, we only have the fields that are grouped. Those are the only fields that are available. And what we could do is aggregate. We can calculate aggregations of the other fields, right? Maybe we can calculate the total number of amount of money that we have raised this quarter, right, or this semester, so we can do a party at the end of the semester. Maybe we can calculate the average grade that we got in this particular course or particular quiz. We can group by quiz, right, and see how we did in a particular quiz. So this is what GroupBy allows you to do, is collapse them into one single record. The aggregate functions are the ones that can operate on the fields and aggregate them as averages, minimums, maximums, summations, count. So let's look at an example. Here we are looking at the student table, and the student table has a field called major ID. Right? So here are all the students across the entire school, university. Right? So you have students from chemistry, from mechanical engineering, electrical engineering, computer science. They're all in the same student table. Right? But I might want to ask questions about a particular, or I want to ask it about a particular department. Right? So I can group them by major ID. So all 1,000 students in computer science would be collapsed into a single record. Right? And then so once they're collapsed in a single record, I can ask questions, I can only ask aggregate questions about the fields because the original fields are gone, right? Their individual values are gone. I don't have them, right? I can only ask aggregate questions about them. I can say, well, what's the minimum graduation year? What's the maximum graduation year? Notice that some aggregate functions might make no sense to us, right? For instance, what's the average graduation year? Maybe that makes sense, right? We might want to. We might also want to calculate this whole bunch of aggregate functions. We can count. We can do the summation, the minimum, the maximum, the average, right, across a group. So here's a simple example of a student table. We have nine students across 3 different departments whose IDs are 10, 20, and 30, which are rendered here in different colors. So we have Joe, Max, and Lee are in department 10. We have Amy, Sue, Kim, and Pat in department number 20. And we have Bob and Art in department number 30. So if we group them, we could group them in different ways. We can group them by graduation year. We can group them by major ID. And we could do all sorts of things. Some groupings might make no sense. Grouping by student name. That might make no sense, right? We are all unique people, hopefully unique usernames. So we are a group of 1, right? Just me, myself, and I. So if we group by major ID, here I have rearranged the records only for convenience, right? So that they are graphically more striking. I've grouped all folks from major ID 10 at the top, major ID 20 here in the middle, and then major ID 30 at the bottom. Once we've grouped them, we can ask questions about the aggregates of all the other fields. Maybe we can aggregate the graduation year. It might make no sense to aggregate the IDs, right? It makes no sense to add them up or average them out, right? There's just unique identifiers, right? That makes no sense to operate on them at all. Same thing, we might make no sense to aggregate anything about the student name, right? We can't, maybe we can count how many there are, perhaps. That's all we could possibly do. Makes no sense to do the average or the max or the min, but we could perhaps count how many there are. There's 4, 3, 2. But we could aggregate, for instance, the graduation year. We could say which is the maximum, which is the minimum, which is the average. The summation might make no sense, right? To add up the graduation years, that has no logical sense to add them up. But yes, average, min, max, things like that. So here this query was that we were calculating the minimum of the graduation year and the maximum. So in the groups now it's graphically obvious which are the minimums and the max. Here's the 2 minimums, right? 2001, the maximum is 2005, minimum is 2004, maximum is 2005. So they're represented here, right? So there they are, the min and the max for either one of the major IDs. And notice that at this point, once we've aggregated them, right? There's no point of asking anything about any individual record, right? All the records have been collapsed in here, right? They're all living in there, but we don't have access to any of the records in there, any one particular record. They're gone. A couple other ones where we want to count. Here we're counting how many student IDs there are, and notice that we are grouping by both the major ID and the graduation year, meaning where are they both the same, right? If they are both the same, then they belong to the same group, right? For instance, here, if we go back, we see that, let's see, where major ID is the same with graduation year, the combination of the two. Notice that we have 2 records where major ID 1, major ID 10, and graduation year is 2004. We have 2 records there. So this becomes one group, right? This becomes one, so a group of 2, group of 1, group of 1, group of 1, group of 2, group of 1, and group of 1. Right? We're considering where these both are the same, right? Where these 2 are the same as these 2 are the same, right? So they belong to the same group. And then we can do aggregates such as count. How many are there, right? And we count here. We're counting the student ID, right? We're counting something that we can guarantee that is not null, right? If we're counting things that were null, right? Maybe you might have here a phone number or license plate or something, some other record that might be null, right? Maybe I don't have a car, right? So I don't have a license plate. So it might make no sense to try and count license plates because some of them might be null, right? So whenever we count, typically we like to count fields that are guaranteed not to be null, right? Such as the IDs, the primary keys, yes? Right? And that's exactly what we did here. We're counting, right? We're grouping by major ID and graduation year, and then we're counting how many student IDs there are, right? So we came up with 2 that were 2004 and 10, 2 that had 2001 and 20, and everyone else was just counted as one group, one element in that group. Make sense? All right. So yeah, so that's there we go. Yeah, same thing. Notice that if we don't provide a grouping, any fields, right? The interpretation is that the entire table is one single group, right? So for instance, that the student table is one single group. In this particular case, in that group, we're asking aggregate, which one is the which one is the minimum graduation year, right? And this is going to consider the entire table as one group and finding what's the minimum overall, the entire list of all the students. If you don't provide a grouping, basically you'll get the same value across the entire table. Okay. This thing. So you might have repeating values that you might want to count just distinctly, especially if you have things that repeat over and over. You might want to skip over things that are repeating. So you have distinct versions of each one of the count and the sum. That you want to skip over repeating values. Obviously, null values are not counted, so make sure that you select fields that are guaranteed to be not null. Here's an example of using GroupBy to calculate a couple of things. So, for instance, one of the questions is, the most A grades in any section. Right. So across all sections, I'd like to know which section, right, had the most grades, most grade A. Right? So in the first query, we retrieve the enrollments that only have a grade of A. Right? So here's from the enrollment table, right? We are retrieving those enrollments where in a particular section we have a grade A. So notice that we have 1A in section 13 and 2 A's in section 53. Right? So that's from the enrollment table, the first query 18. Then we can group by the section ID and count how many enrollments there are. Right? So we group by section ID. Notice that this is one group, 13, and this is another group, 53. Right? We can collapse these two, collapse this one, and then count how many A's there are. Right? So there's 2 here and 1 here. So we end up with the section ID and then the count of how many there are. Right? We can then do another group. Right? We can group the Q19 with itself, right? And then just group the entire table. Right? We don't want to group any particular field. So consider the entire table. Just go across all the fields, all the values in that particular across all the records, and find which one is the maximum. In this case, is number 2. Right? Right. So two group bys to be able to find out which one is the maximum across all the sections. Make sense? Right. You can graphically represent the same thing, either in a nested set of queries, group by, having retrieved the query of the selecting all the grades equal to A. So either nested or as views, or also as graphically like this. Okay. All right. So joining. Let's talk about joining. So joining, as I mentioned earlier. Right? It starts with product. Product being the considerations of all possible combinations across multiple tables. Here you have tables A and B having values A1, A2, B1, B2, and the cross product of A and B is basically all possible combinations of the records. Right? Record A1 with record B1, record A1 with record B2, and then you iterate over the record A2 with B1, record A2 with B2. All right. So product considers all possible combinations. Some of these combinations might make no sense, right? For instance, considering me as a faculty, with some college that I don't teach at, right? And so it'll combine me with chemical engineering and electrical engineering, and all these colleges that I just don't teach there, right? But product considers all possible combinations of say, all faculties with all colleges. Yes? Right? Then combined with that, so here's a graphical representation, right, where we have here just a long list of students. Let's consider just only the first 3 students here. Combine them, doing the product cross product multiplication with the departments over here on the right-hand side: computer science, math, and drama. If we do the cross product, what we end up with something like this, right? We have Joe, Amy, and Max repeated multiple times, combined with all the departments, right? Notice that some of these combinations absolutely make no sense, right? Notice that the first one makes sense. We have Joe actually enrolled in major ID 10, right? So when you combine it with computer science, which is major ID 10, it makes sense. But the fact that Amy is matched with computer science, that combination makes no sense, right? The third one either, right? So only 3 of these make sense, right? Only where the major IDs match, where the major IDs match. That's where the select comes in. That's where the select comes in. And we are feeding the product into select, right? And then we're filtering out only where the primary keys and the foreign keys match, right? And we highlight here the ones that do match, and we would ignore the ones that don't match, right? Now this is such a useful and common operation that you do a product followed by a join, right? That we give it its own specific name called the join, right? And it has its own equation representation, and it has its own operator, the join. The join takes 2 tables as argument, and then the predicate that joins the 2 tables, right, of where the primary key and foreign key reference each other. Okay. A couple other examples here. We are joining a couple of tables here. We are first retrieving the student whose name is Joe. So grades that Joe received in his course during 2004. So first we retrieve Joe, record of Joe, and then we join the student Joe with the enrollment so that we can retrieve all the sections where Joe was enrolled. We then filter from those sections where the year was offered 2004, and we join those sections with the enrollments that Joe was enrolled in, right? And then we retrieve the grades for that join. Okay. Or graphically, we can represent it this way, right? Where we have a flow of data from the various tables, feeding all the way up to the ultimate query of identifying what the grade is for Joe enrolled in sections of 2004. Okay. Here's another example. There's a couple examples that you might want to go through. Joining employee and department along the department name. So we have finance, sales. Notice that there's no production. So these are foreign keys, primary key. So they come up like that. If we go back to the original example before, where we were calculating the number of A's, right? Originally we had calculated the maximum number of A's, right? And we had come up with 2, right? So we could specify additional questions such as, well, now that I know the maximum number of A's is 2, I'd like to know which section gave out the most A's, right? Well, what we could do is just join these 2 now, right? Because we calculated the maximum of 2, we can join Q20 alongside with Q19 with 2 equal to 2, to find out that it's 53. Some folks might say, well, when we were calculating this 2, couldn't we have also provided here the 53? That would have been very convenient, right? If that 53 over here on the section ID would have lived enough to be able to just pop it here, right? Well, it's not, right? Because it's since we are joining, since we are grouping the entire table, right? All the records that are used in the grouping, right? the values that are not being aggregated are lost. Right? So that particular 53 is gone. Right? So we don't have access to that. So the only way is to join these two together and retrieve the section that way. And this is exactly what we have here. We have the joining of Q19 and Q20 to retrieve the section that has the most A's. Okay. All right. Let's